Good morning. Thank you for being here, and thank you, the organization, for inviting me. Today I'll talk about dynamic multiscale spatial temporal models for Poisson data. And this work was joint work with Marco Ferreira. He is in Virginia Tech now. So I'll give some introduction on this decomposition, the multiscale decomposition. Then I'll talk about the dynamical temporal evolution that we are proposing. And we are going to highlight some advantages of this modeling. So we are able to deal with very large data sets. So it's scalable. We can parallelize all the estimation procedure. And I'll show you the first application, tornado data. And I have another application, mortality, which shows a different aspect of the modeling, but I think I'll not have time. So the main goals are first to develop a flexible spatial temporal model for count data, to provide estimation procedure which is scalable, so we are able to deal with very large data sets. We want to compare this proposal with known models for this kind of data, so we have compared the model with dynamical Poisson models and with the CAR model, where we included temporal and spatial random effects. So that's the usual model for this kind of data. So we are going to put together two things. First, the multiscale Poisson factorization, which allow us to deal with spatial structure. And then we are going to propose a Dirichlet temporal evolution for this model. So we are going to do these two things together, and we expect, and we actually get, spatial temporal dependence. So we can measure that, and we are doing both things together. So the multiscale data, it's this kind of data. So we have a region of interest which is divided in subregions. Okay, and these subregions can be divided again and so on, so we have scales of resolution. Okay. So the spatial partition, it might be that we have, because of confidentiality, we have data only up to certain resolution, so we cannot have more detail. And another example, we can have a point process as well, but we have computational limitations sometimes, and instead of modeling the actual point process, we are going to look at aggregated counts. So we put together in bins and look at the counts for these regions. Okay, so these are two examples. So here we have actual a division for the country, for the counties, and here we divide depending on our interest. Okay, so this is a possible division. So here I have our problem. We have a non-homogeneous Poisson process with a certain rate, which we call lambda S. And this is the domain we are interested. And we have data only up to a certain resolution. We call this L. Okay? And for each subregion, we are going to observe a count. So we divided the region in subregions and divided again up to a certain resolution, and then we have the counts for each bin. Okay, so this is our data. And for this data, we are interested in modeling the spatial dependence and the temporal dependence. So the previous proposals in the literature, we have this paper, this chapter actually in a book. They are doing hierarchical modeling for turbulence, and they use wavelet decomposition, and the underlying process has coefficients which vary through time. It's allowed to vary through time. This other work in 2007 proposed also a multiscale decomposition. We have aggregated level, and we go down to detailed levels. And for each level, it's allowed just a fixed number of children, so this is a limitation. And the temporal dynamics are only put in the most aggregated level. So we don't have on the other levels temporal dynamics. Okay. In 2010 and 2011, Marco Ferreira, he proposed a multiscale dynamical spatial-temporal model for Gaussian data. So he was assuming Gaussianity, and the number of children is allowed to vary, so it's not fixed. It's flexible in this way, and the dynamics are put in all the resolutions. So in the most aggregated one, and on the other levels as well. So we are now trying to, we did actually, the same kind of modeling, but for Poisson data. So if you have counts, it's expected that if you divide the domain, you are going to find low counts, right? If you divide and divide and divide, at some point you have low counts, so you are not able to use the Gaussian approximations. So for several applications, you are not able to use the Gaussian approximation for the modeling. So for these cases, we are going to propose this other model. So this is the decomposition was proposed in 2001. So you get a count for the parent, and this count is divided for the children, okay? And one of these children is the parent, and has more children, and divided again this count, and so on. And this is done through this model. So you have the model for the most detailed level, given the mean, the rate, and this is decomposed in all these resolutions. So we have here the model for the most aggregated level, which is Poisson. So you have a Poisson model for the counts, and then for the children, you are dividing a total that you know. Okay, given this total, you have this partition. And in this case, the model is multinomial, right? So you decomposed a large problem with many parameters in smaller problems. For each level, you have a small problem, okay? And on the first level, you have a Poisson model, and on the other levels, you have multinomials. So this is the multiscale factorization. The parameters are the rates at the most aggregated level, and the weights in each level of resolution. Okay, so these are the important parameters. How you divide the count for the parent for the children. Okay, so this is the important parameter. Okay. Now the next step is to model the spatial-temporal dependence. We are going to construct the model in a way that we are going to achieve posterior independence between blocks of parameters, so you can parallelize the estimation in these blocks, given this multi-scale decomposition, right? And for the most aggregated level, this is already known in the literature, so you can do a beta evolution for the parameter for the rate. So you have the rate at time t, it depends on the rate on the previous time, And you have to make it evolve over time somehow, so we have this error, let's say, eta is an error term, and it's beta. So if you take the log in this equation, you can see it's kind of similar to the Gaussian evolution when you have the mean is function of the mean in the previous time plus an error. But here is in the log scale. So this is well known. Was proposed by Smith and Miller in '86. So this is the model we use for the counts, for the means in the most aggregated level. So the modeling in this level was already done. For the rates, in this case, we have this parameter here, which we called gamma, which is the discount factor. Who works with dynamical model knows that the discount factor is very important. So if it is close to 1, you don't have much, you don't have change over time. So it's kind of stable. The process is stable over time. You can see that here. So if you take the expected value of this part here, it's 1. So lambda t is the expected value is the previous rate. So it doesn't change much. On the other hand, if you take gamma going to 0, you have a very large variance, and you have change over time. So it's accommodating all kinds of behaviors over time. So this is for the most aggregated level, the Poisson model. When you go to the next level, you have, as I said, the parent has a count. You are dividing this count for the children, and you have the proportion that you give for each children. This is the parameter of interest for each subregion, of course. So how can I do the temporal evolution in this case? We have a vector of parameters, and you want to make this vector evolve over time. In this case, this vector omega is going to evolve according to this equation. So this is the way you have to define the temporal evolution so that you have conjugacy afterwards. So you have multinomial, you're going to conjugate it with Dirichlet, and you're going to get Dirichlet again. So this is going to allow us to do everything in closed form. You don't need to do simulation. Okay? So to do that, you have to define the equation this way. So the vector depend on the vector on the previous time, and here it's a sum, it's a random sum, and here is a vector of errors, let's say. Okay. And these errors are independent and beta distributed. Similar to the previous case, it's also beta. So here we also have discount factors. We're going to call delta, so it's clear that we are talking about the other levels of resolution. So we have deltas for the level 1, 2, and so on. So we can always define the discount factors. They are here on the beta distribution, okay? Once again, if you have delta going to 1, it means that there is not much changing over time. And if you have delta going to 0, you have changes over time and everything in between. So this is going to be useful because if you have a very large data set, you're going to have many lambdas, and you want to look at the ones that are more important. So the regions, the subregions where you have changes occurring. So in these situations, you are going to, where you have very large data sets, you are not able to look at all the parameters and check which ones are the most important. So in order to simplify the work, you can just look at the posterior distribution of the discount factors. So if you have deltas that are much smaller than the others, it means that something is happening in this subregion. Okay, so this highlights the subregions that are more interesting. So if you have a very large data set, you are not going to look at all the posteriors, you just go and check the ones that are more important. So that's what we suggest. Okay, so as I said, we defined the model in a way that we are able to have posterior independence between groups of parameters, so we can parallelize the inference, and we can do this very fast for very large data sets. So the lambdas are independent of the omegas in the next level and the other levels. So all the levels are independent a posteriori. How we do inference in this case? I'll try to summarize. So if you assume that the priori is gamma, for the most aggregated level, you know that you can conjugate Poisson with gamma, and you get a posterior that's gamma. Okay, so here you have that the posterior for the rate is gamma, using the evolution that Smith and Miller proposed. Okay. You get the same for the most detailed levels, the other levels of resolution. So if you have a multinomial, you can conjugate with Dirichlet, and you get Dirichlet again for the omegas. And this is achieved because we define that equation of evolution for the parameters. Okay. So we are not only interested on this posterior sequential inference, we also want to to know what's the posterior for the rates after observing all the data. So here we have given all the data points, all the times, you can find the distribution for the rates at the most aggregated level. And this distribution is also known, it's a gamma, kind of gamma. It's dislocated, but it's gamma. And for the Dirichlet part, for the most detailed part of the model, you have that you need a multivariate distribution, so you have the vector omega, and you have also the sum of the weights, it's S, which is also random. So you have there, well, it's well defined, it's a beta for the sum, and here a modified Dirichlet because it's dislocated, it's not from 0 to 1 for its value. Okay, so it's just a modified Dirichlet. So all the distributions are known. So in this step of the inference, you can simulate from well-known distributions. It's not that you need rejection, sampling, or anything like that. So we have a composite approach. If you are doing a conjugate analysis, you know the predictive distributions, right? So for the most aggregated level, you know what you get when you have Poisson data with gamma priori. Right? So you know the predictive distribution. So all the hyperparameters can be estimated from this marginal distribution. You integrate the parameters and just look at the hyperparameters. Okay, so this makes it much easier. So the discount factors are these hyperparameters, which you can easily estimate doing Newton codes or things like that. You don't need to do rejection or MCMC. So we tried Newton codes, we also do MCMC at some point for one application because we have also included covariates. So we have a regression in the most aggregated level. So we have some parameters and we did it doing SEER and MCMC, but you don't need to do that. So we have a composite approach. First, we simulate the discount factors or estimate it from the marginal posterior distribution. And then, conditional on these values, you simulate the spatial temporal multiscale coefficients using this sampler, forward filter, backward sampler. Okay, so you just get the parameters and then you do the filtering using that dislocated gamma and dislocated Dirichlet. So as I said, it's computationally very efficient. I hope you agree with me. So I'll just skip this part. And I have an application to the tornado data. Here I have reports from 1953 to 2010 in the US, and this is the region of interest. We just focused on this domain here, a regular domain, which is known as tornado alley. We've also just looked at the most intense tornadoes. So on the scale, we just select the ones from F3 to F5. And the first touchdown, so we just take the time of the first observation. So because the tornado keeps going, so just the first touchdown. We have divided the region. So this was my decision. I decided to divide this way. So I have first divided in 4 regions, then each region in 4 again, and then in 4 again. So I have 3 levels of resolution, let's say. So we included also the El Niño and La Niña effect. So that's why I have covariates, and I have beta regression coefficients to be estimated. So in this step, I did importance sampling, or I did MCMC as well. You can choose your method to estimate the beta coefficients. And here I have, first, let me show this one. I have the discount factors, which are the important main parameters. So here you can see the deltas for the first level. Two of them, for 2 subregions, are very high, but you can find 2 here that are smaller. So that are the ones that I'm going to look closely. So I looked at the children of the 3rd region. So I had 2 there to choose. I looked at the 3rd. And you can see again that you have the discount factors for the children. And most of them are high, but there is one that is smaller. So once again, I just looked at the children of this subregion instead of looking at everybody. So the children have these omegas, the estimated omegas. Here are the credible intervals across time, okay? And this is the first child, and so on. And you can see that if the division, the partition was equal, you would have 25% for each, right, across time, if nothing was happening. And you can see that for this one is what's happening. It's around 25%. But here, for example, the probability that it's higher than 25% is 9.96. So it's very high. So there is something happening here, and there are news, and we found some historical background to support this. That's 1990. Okay, so there is this sub-region that there is something happening there. The rates are changing. It's going up and then down. And here as well, it's almost always higher than 25%. Okay. So as I said, I compared with the usual way to model this kind of data, using the CAR model with spatial temporal Brownian effect. And our model is doing much better. And it's much, much faster. There is no comparison. Okay, we can do that in seconds, in the same computer, of course, and the CAR takes hours for this kind of data, this size. So I use it INLA to do the CAR part. Okay. So I have here just, okay, I'll just skip this. This is a mortality application where you can see doing this discount factor analysis, some regions, you can highlight the regions where the rates are going down very quickly. So it's easy to identify this kind of region. This is an example where there is not much change, but here it's changing a lot. Just to conclude, we proposed a way to model Poisson data in which we are able to model spatial temporal dependence. It's not clear from what I said that you were doing jointly, spatial temporal modeling, but it's in there. We have some results in the paper where we show the spatial temporal covariance between points, and you can see that it depends, because it goes through the father to the children, and at some point you have a common father, and the time is evolving for all of them together. So it's being done jointly. So you have a way to detect interesting regions in a very large data set, which is useful for applied sets. You can make maps of risks, everything that you do for Poisson data. It's all there. And we are trying to extend this model, for example, to accommodate the fact that I had to choose the partition in space, right? And this will define low counts at some point, right? So when I stop dividing, this is a question. So that's what we are trying to model now, to let the data say when you stop dividing. Okay, so that's it. Thank you.
Thank you, Tait.
What effect does the partitioning have on your results, and what effect does the partitioning, the initial partitioning has on your results, and can you do like county level stuff, I mean, which may be geographically more relevant than just making it a square or a rectangle?
The mortality application is divided like that, right? It's a management divided. It's not like I didn't do it. But because of confidentiality, probably, I don't have the more detail. I just have on the county level.
So just elaborating a little bit more about that. Did you ever try what happens if you change your partitions? For instance, in your tornado data, I assume there's kind of like arbitrary, at least in some regions, you can group things in different ways and see what happens. And that triggers another possibility that actually you make inference on those subsets. That's the...
Thank you for your question. That's what we are working now. I do several possible divisions. I rotate the system, and I do model averaging to accommodate this kind of uncertainty. Okay, so this is the kind of work that Cressy did for global data in the globe. So that's what we're trying now.
Yeah, very nice work, Thijs. On the multinomial Dirichlet as decoupled into Poissons and gammas, when you use the stochastic volatility, the gamma beta evolution model, a problem arises when some of the rates vary more dramatically than others. To recouple back to the Dirichlet, you have to have the same shape parameter in each of the gammas. So you have to have the same value of the discount factor across the cells that make up the multinomial. So I can imagine that some of the cells, the rates are varying wildly, and some are quite constant. So you would sort of blur the lines in choosing an optimal discount factor for that. I wonder if you've thought about that.
For one parent, I have the same discount factor, but for the different parents, I have different discount factors, right? So I have the number of discount factors is the number of parents, right? They might be very different. I showed there the example where I had two, which the rates were kind of constants. The weights were kind of around 25%, but the other two were very different. One was compensating the other and changing a lot across time. Yeah, this might suggest that I should divide more, maybe. So this other work that we are doing, in which we are trying to let the data say when I divide or not. So this might help, because then I have, if I need more division there, I will have. If I don't need, then I can just segregate. So I think this will accommodate this kind of problem.